In this month's chemical calculations video, we're going to look at how we derive units for equilibrium constants, particularly Kc and Kp. So the first thing we really need to get this right is a little bit of maths background in how we use indices, how we use powers that things are raised to. So we need to think about what we do when we divide things that are squared or cubed or to the power 4 or whatever, what we do when we multiply them, and how we express that as well. So let's say, for example, that we had x to the power 4 and we divided it by x to the power 3. So what we're doing there when we divide things that are to the power is I've got x times x times x times x divided by x times x times x. So I'm just going to cancel them out and I'm left with x. Or the other way to look at it is I'm left with x to the power 1. We don't always write that 1. And the way that came about is I did 4 minus 3. Let's do another example. Let's do it slightly different way round. What if we had x cubed divided by x to the power 5? Okay, so again, I'm going to take the top number, the top indice, I'm going to take away the bottom number. So 3 take away 5, I can write that as x to the power minus 2. Alternatively, that is 1 over x squared. So let's leave it as x to the power minus 2 because that's how we're going to be expressing these units. You've just got to try and get used to this idea of this is what it looks like. So there we did the top take away the bottom. So here we did 3 minus 5. That gave us minus 2. What about if we multiply things together? So let's say we had x squared times by x to the power 6. Now we do not want to multiply them together. It's not going to be x to the power 12. Because if you think about expanding that term, what you've got there is x times x, that's x squared, multiplied by x times x times x times x times x times x. So what you've got is x times by itself 8 times. So what I'm going to do here is add together the indices to get x to the power 8. So we know that we can write things in terms of to the power minus numbers. What that actually means is 1 over x squared. We can write them to the power of positive numbers. If we had, for example, x cubed multiplied by x to the power minus 5, again, I'm going to add those together. So that is going to be 3 take away 5, which is going to be x to the power minus 2. And in fact, x cubed times x to the minus 5 is the same as doing x cubed divided by x to the 5. And that's why I'm doing 3 minus 5. Okay, let's take it away from x and try and apply this to a bit of chemistry, in particular Kc and Kp. So if we had a chemical equation, I'm going to make one up. 2a plus b makes c plus 3d. There we go. Okay, so how does this work if I was writing an equation for Kc? C stands for concentration, which means that I'm expressing everything in terms of the concentration of these substances, and all of our equilibrium constants are written as the products over the reactants to the power of the numbers in front, the sort of stoichiometry in the balanced equation. So at the top I have concentration of C. There is no number there, so it's to the power 1. I have concentration of D, and that is to the power 3. I have concentration of A to the power 2, and I have concentration of B which again is just to the power 1. Okay, so how do we get from there to finding the units for KC? So there is a very long way round and there is a super short way round. So the long way round is when you write it all out. I've got moles per dm cubed times moles per dm cubed times moles per dm cubed times moles per dm cubed. So what I've done there is I've done moles per dm cubed for my C, and then I've done it 3 more times because it's multiplied by itself 3 times. And then on the bottom I could write moles per dm cubed times moles per dm cubed, because that's my A squared, and then times mole per dm cubed again. And notice, by the way, that we write mole per dm cubed, the reason it's written like that is because what we mean is moles divided by decimeters cubed. 1 over dm cubed equals dm to the power minus 3. Okay, and then you may have been taught to do the cancelling out, so I can cancel those. They're the same, they're the same, they're the same, they're the same, and I end up with one thing on the top, and then that's all I have to do is it's moles to the dm cubed to the power 1. So that was fairly easy. However, if I had a different equation, for example, A over C squared D, totally making up my reactants and products all the wrong way around now. So if I do that, I'm then going to end up with a lot of moles per dm cubed on the bottom. So what we're going to do in this method that I'm going to show you is moles per dm cubed is constant. It's not going to change at any point. All the units of concentration are the same. So on the top, I just have moles per dm cubed. Humour me, going to put it in brackets and put to the power 1. And then on the bottom, I'm just going to count what I've got. Well, I've got 2 lots of C, 1 lot of D. So altogether, at the bottom, I've got moles per dm cubed to the power 3. We know how to divide powers. We do the top one, take away the bottom one. So that is equal to moles per dm cubed, put it all in brackets, to the power minus 2. 1 take away 3 is minus 2. That's a 1 there, remember. So remember, when there's not a number, there is a 1 there. Okay, what do I do now? Well, when you do a power to the power of something else, you don't add it anymore. This is the time when you multiply. So when we multiplied powers together, like at the bottom where we had C squared times D, we ended up with the whole thing being cubed. So 2 plus 1. Now we've got moles to the power 1, also to the power minus 2, and we've got dm to the power minus 3, and then that is further raised to the power minus 2. So we're going to multiply those numbers together. And so the units would be, take my 1, times it by minus 2. 1 times minus 2 is minus 2, so moles minus 2. Take my minus 3, multiply by minus 2. dm to the power plus 6. So that felt like I may have taken a long time to get there. So how could we simplify this even more? Well, we know that the reason that this is to the power minus 2, and that's all we actually need to know, is because there was one thing on the top, my A, and there were 3 things on the bottom. The top is always my products and the bottom is always my reactants. So all we actually need to do is do how many moles of products minus how many moles of reactant, take my moles per dm cube and raise it to the power of that number. So let's do that as some examples. Here are loads of different equilibria. Some of them are gas, some of them are aqueous, but we can do KC for any of those because they all have concentration units. Okay, so the first one, I have 3 moles of reactants, 2 moles of products. So I am going to do 2 minus 3 reactants on products on top. That'll be the 2. 2 minus 3 is minus 1. So I'm going to take moles per decimeter cubed and raise the whole thing to the power minus 1. So 1 times minus 1 is minus 1. Minus 3 times minus 1 is 3. Okay, let's have a look at the next one. I have got 3 moles of products, 3 moles of reactants. 3 take away 3 is 0. Anything to the power 0 is 1. So here there are no units. So the units cancel out for this one because I have the same number of total moles on each side of my equation. Next one down, I have 2 moles of products and 3 moles of reactants. That is exactly the same as the first example. 2 take away 3 equals minus 1. My units will be moles to the minus 1, dm to the power 3. Next one down, I have got 5 moles of products, 1 mole of reactants. 5 take away 1 is 4. So let's get this in brackets. Mole to the power 1, dm to the minus 3. Everything is raised to the power of plus 4. 1 times 4 means I have moles to the power 4. Minus 3 times 4 means I have dm to the minus 12. That's quite an unusual one. Next one, I've got 2 and 1. 2 take away 1 equals 1. My units don't change because I'm just doing them to the power 1. Next one, I have got 3 and 3. So I have no units. So that's how we apply that, and that's how we really easily work out the units for Kc. So Kc, remember the C stands for concentration. What about Kp? Well, it's even easier. All the same principles apply. I'm still going to do products divided by reactants, but I'm now going to have, instead of units of concentration, units of partial pressure, which are the same as units for pressure. So pressure, depending on your exam board, can either be in atmospheres or kilopascals, or it could be in pascals. Yeah, it could be in anything, because this method works no matter what the units are, and it's even easier because all I have to do is the same technique as before. So if I look at this equation, 2 moles of products minus 3 moles of reactants gives me minus 1. So my answer would be atmospheres to the minus 1, or if I'm given pressure in kilopascals, kilopascals to the minus 1. Next one down, I've got also 2 minus 3, same units, atmosphere minus 1, kilopascals to the power minus 1. Next one, I've got 2 minus 1, give me 1, so my units are just atmosphere and kilopascals. And the great thing about this method is even when you've got a stinky little equation like this one down here, which is really complicated looking, but it isn't complicated looking if you can just take some numbers away, which I'm pretty sure you can. So just adding and taking away. On the right hand side, I have a total of 10 moles of gas molecules. On the left, I have 11. So actually, it's just 10 minus 11, which is minus 1. And unexcitingly, the units are simply either atmospheres to the minus 1 or kilopascals to the minus 1, depending what the question gives me. So even though it looks confusing, it's really no different in the maths. Just a final little consideration is that those were all very unique equations that could have any numbers of reactants and products. So Kc, Kp can refer to any chemical reaction that involves concentrations or gas pressures at equilibrium. Whereas Ka and Kw are always in the same format, so they will always have the same units. So when we think about Ka, for example, we may have a weak acid like ethanoic acid dissociating to make H+, and the ethanoate iron, or we could write that as HA dissociates to form H plus and A minus, and we can use that shorthand for any of our Ka equations. So that means that Ka is going to be products over reactants, still going to be measured in concentration. Oops. And so there are going to be two things on the top, one thing on the bottom, 2 minus 1. So basically, it's just going to be moles per dm cubed. The units cancel out, you just end up with one concentration unit at the top. Kw, however, is different, and that is because when water dissociates, we need to be a little bit careful about the state symbols. So water is not dissolved in itself, it is just itself, it's a liquid. And when it dissociates, it does form ions which are dissolved. So the H plus and the OH minus have a value of concentration that can change, but the water can't change its concentration. You can't add more water to dilute water, it just stays a fixed concentration no matter what the conditions are. And so that means that we don't include it in the Kw because it won't affect the impact. The position of equilibrium. So Kw is sometimes called the ionic product of water for that reason. We mean product here like maths, when product is two things multiplied together. And so because Kw has that form, it's actually going to be, there's two products, effectively there's no reactant. So it's going to be moles per dm cubed squared, which means that the units would be moles squared dm to the minus 6. Now you're actually given those units most of the time in the question or in the data book, but paying attention to them will hopefully remind you of the format of the Kw equation.